Multivariable Calculus, Section 12.2, Functions of Several Variables. 2 dimensions. Recall back in single variable calculus and in pre-calculus we defined functions in a single variable, f of x, to be an expression in x. For example, we could have f of x equal the square root of x. And we start with the domain, the set of real numbers or a subset of the real numbers, and we take an x value and we map it or assign it to a y value, which in this case would be the square root of whatever x value we chose. And then in order to see a picture or a graph of the function, we drew a y-axis perpendicular to the x-axis and graphed several points connecting them with a smooth curve. So in this case, the domain and range are both the set of real numbers that are greater than or equal to 0, or the non-negative real numbers. Notice that the domain of a single variable function is one-dimensional, whereas the graph is a curve drawn on the two-dimensional xy plane. So now we're going to move into 3 dimensions. A function of 2 variables is an expression in x and y. For example, we could have f of x comma y equaling the square root of x times y. Now in this case, in order to take the square root, either both x and y have to be positive or both x and y have to be negative. Now notice that in this case we have 2 independent variables, x and y, because we can choose any values that work, whereas we have still have one dependent variable, namely z. So in this case, the domain of this function are the set of points in the xy plane such that x and y are both positive or x and y are both negative. In other words, the first and third quadrants of the xy plane. Now if we rewrite it as z equal to the square root of xy and square both sides, keep z squared a particular number, and we get a hyperbola. So anywhere where we would draw a trace of the surface, which would be the graph here, we're going to get a hyperbola that gets wider as z increases. So the graph is half of a hyperboloid of 2 sheets, and you only get half because in this case z is always going to be greater than or equal to 0. Notice that the domain now is 2-dimensional. It's a subset of the xy plane. And the graph is a surface drawn in 3-dimensional space rather than a curve drawn in 2 dimensions. Here's a picture that I found online. Someone's attempt to show the pink rectangle is a subset of the xy plane, and it's being mapped onto the purple surface. In 4 dimensions, we have functions of 3 variables, which would equal an expression in x, y, and z. The domain is going to be 3-dimensional. So it's going to be part of a solid or a surface or part of 3 space. And the graph can't be drawn very easily because it's 4-dimensional, and so we're not going to be drawing any 4-dimensional graphs. Here's an attempt made that I found online to show a pink space object being mapped into a purple space object. Here's an example of a function in 3 variables. X, y, and z are independent variables, and usually we call the 4th variable w. It would be your dependent variable. Now if your dependent variable is 0, then x, y, and z would have to be 0, and so you would just get a point at the origin. And if w were 1, you'd get a sphere of radius 1 centered at the origin. And if w were 4, then you would get a sphere centered at the origin with radius 2, and so on. So as w gets bigger, the sphere gets bigger. And so we get infinitely many spheres of however many radii you would want. So since x, y, and z can take on any values, the domain for this function is all of x, y, z space. Now if you wanted to graph this in 4 dimensions, what you could do is think of w as time. So as time progresses from 0 on up, you get a sphere of larger and larger radii. So you could think of the graph as a movie. Let's look at that again. But to draw it in 4 dimensions is pretty much impossible. Here's some vocabulary. Here we have a surface that could be a picture of a function in two variables. In the first picture, we have what are called traces. If you were to slice the surface vertically, perpendicular to the xy plane, then the shapes look like they'd all be parabolas. And those are traces, and we've had that vocabulary word before. Now in the second picture, those are still traces, but in this case, the plane that's slicing through the surface is parallel to the xy plane. And when the plane slicing through the surface is parallel to the xy plane, they're also called contour curves as well as traces. And then finally, in the last picture, these are called level curves, and that's where you draw the contour curves, but you draw them flat on a single plane so that you see sort of a two-dimensional image of the three-dimensional surface. Number 2, identify the largest possible domain of f of xy equal the square root of x squared plus 2y squared. So x and y are your independent variables, and z is your dependent variable. Since x squared plus 2y squared is always greater than or equal to 0 for all x and y values, then the domain of this function is the entire xy plane. Number 8, identify the largest possible domain of xy, f of xy, equal the tan inverse of y divided by x. Okay, so tangent inverse of a number returns the angle whose tangent is that particular number. And tangent values run the gamut from negative infinity to infinity. So y over x can take on any value at all. The only issue is that y over x has to be a real number, and therefore x can't equal 0. Now, when x equals 0, what have you got on the xy plane? Because remember, these domains are always a subset of the xy plane. X equals 0 on the y-axis. So the domain is the xy plane minus the y-axis. Number 12, identify the largest possible domain of f of xy equal the square root of 4 minus x squared minus y squared. Well, we have to keep what's under the radical greater than or equal to 0. So if I move x squared and y squared to the other side, then it's pretty clear that this is the inside of a circle. If it was equal to 4, it would be the circle centered at the origin on the xy plane of radius 2, but because it's less than or equal to, we get the interior points as well. So the domain is a subset of the xy plane, as always, namely a disk of radius 2 centered at the origin. Number 14, identify the largest possible domain of f of xy equal 1 plus sine xy over x squared plus y squared. And again, of course, x and y are independent variables. You can choose any values that are legal and then compute the z value that would be plotted above that point on the xy plane. Y and x can't both be 0 because then your denominator would be 0, but you can take the sine of any angle. So that's the only restriction, and therefore the domain is the xy plane minus the origin where x and y are both 0. Number 20, identify the largest possible domain of this function, f of x, y, z, equals the sine inverse of 3 minus x squared minus y squared minus z squared. So basically what we've got here, sine inverse returns an angle whose sine is that quantity, and that quantity then has to stay between negative 1 and 1 because sine values are always between negative 1 and 1. So if we subtract 3 from all three parts of the inequality and then multiply through by negative 1, hence flipping the inequality signs, then we have spheres here. If it was equal to 2, you'd have a sphere of radius 2, root 2, and if it were equal to 4, you'd have a sphere of radius 2. And so what we're getting is the stuff in between those two spheres for our domain. So the domain is a subset of x, y, z space, as always, namely a solid bounded by two spheres centered at the origin of radius root 2 and 2. Now I tried to draw this, but it was a little difficult. So if you can imagine like a ball with a very thick crust and a big hole in the middle, that's what the domain looks like. Number 28, describe the graph of f of x, y equals 16 minus y squared. So the equation is z equals 16 minus y squared. Notice x is not mentioned, so x can take on any value it likes. Now, if z is 0, then solving for y gives us a y equal plus or minus 4, which means there will be two horizontal lines parallel to the x-axis in the xy plane. Now, the biggest that z can be is 16. So when z is 16, we solve for y, we get y equals 0, which would be the x-axis, except we draw it up at z equals 16. So it's parallel to the x-axis. And if we continue choosing values between 0 and 16, we get y equal plus or minus 2 in this case, and so we always get traces that are lines parallel to the x-axis. Now, if we look just at the equation, z equals 16 minus y squared, when x is 0, then we can draw that parabola in the yz plane. It looks something like that. And we get the same parabola regardless of the x value, and so we would get more parabolas anywhere along the x-axis. And so basically this is what our surface would look like. This surface is a cylinder. Its generator is the curve z equals 16 minus y squared in the yz plane, and its rulings are lines parallel to the x-axis. Number 32. Draw some level curves for the function f of x comma y equal x squared minus y squared. Well, the equation then is z equal x squared minus y squared. And if z is 0, we get two lines in the xy plane. So there's one level curve for z equals 0. Choose another z value. If z is greater than 0, for example 1, we get a hyperbola, which would look something like that. Of course, the contour curve would be drawn up at z equal 1. So these are level curves all drawn on the xy plane. If z were 4, we'd get another hyperbola like that, and so on. And so by changing z into various values, we get other level curves. Now, if z is negative, which it could be, then we would solve, for example, if z were negative 1, we would multiply through by negative 1 and get 1 equal y squared minus x squared. So when z is negative, we get hyperbolas on the y-axis. If z is negative 4, we get that, and so on. So we get level curves on the hyperbolas on the y-axis as well. The level and contour curves, for that matter, include two intersecting lines and equilateral hyperbolas that become wider as the absolute value of z increases. Number 40. Draw some level curves for the function f of x comma y equals 1 divided by 1 plus x squared plus y squared. In other words, z equals 1 over 1 plus x squared plus y squared. Now notice that this fraction is always going to be greater than 0 because everything's positive, and it'll always be less than or equal to 1 because the denominator is either 1 or bigger than 1. So for example, if x and y are both 0, we get z equal 1. And that would be a point above the origin on the xy plane at z equals 1. So the level curve for that would just be a point on the origin. Now as z shrinks, for example, if z is 1/2, then the denominator would have to equal 2, which means x squared plus y squared would equal 1. So at z equal 1/2, the contour curve would be a circle, and we draw that as a level curve on the xy plane. If z is 1/4, then the denominator equals 4, and we get another circle whose radius is root 3, and that would be drawn up at just barely above the xy plane at 1/4 for a contour curve, but the level curve is what we draw on the xy plane. So as z shrinks, the circle gets bigger and bigger, but z can never be 0, and so the surface never actually touches the xy plane. As z goes to 0, the circle grows, but never touches the xy plane. Number 44. Describe the level surfaces for f of x, y, z equals z squared minus x squared minus y squared. So let's call our dependent variable w and our independent variables then are x, y, and z. Well, let's look at some examples, some specific surfaces. For example, if w is 0, we get this, and solving for z squared, we get z squared equals x squared plus y squared. Now, if x is also 0, then we get z squared equals y squared, or z equals plus or minus y when we solve for it. So in the zy plane, this is a trace of the surface. Now, if z squared is a positive value, then other than 0, then we get c equal x squared plus y squared, and that of course would be circles. So we get circles parallel to the xy plane at various z values. And so if w is 0, then we get a surface that is a cone. Now, if w is greater than 0, then we get c equals z squared minus x squared minus y squared. And if you look at your handy-dandy reference sheet, that would be a hyperboloid of 2 sheets around the z-axis. And if w is less than 0, then we would multiply through by -1 and get a positive value equal x squared plus y squared minus z squared. And again, if you look at your handy-dandy reference sheet, this is a hyperboloid of 1 sheet on the z-axis, where the circle on the xy plane would have a radius of square root of c. So the level surfaces for this function consist of a circular cone when w equals 0, hyperboloids of 2 sheets when w is positive, and hyperboloids of 1 sheet when w is negative. And all of these would be around the z-axis. Number 50, match the function of x and y equal x squared minus y squared with one of the graphs shown below. And so if you write it as z equals x squared minus y squared and look at your handy-dandy reference sheet, you'll see that the shape here is a hyperbolic paraboloid. And only one of these graphs looks like a hyperbolic paraboloid, and so it has to be 12.2.27. Number 52, match the function in x and y equaling this expression to one of the blue graphs shown below. And here are the same graphs again. Okay, so we have z equal to this expression in y and x. If we hold x steady and look at the function in just z and y, we get a cubic function. So that's what a cubic function looks like. On the other hand, if we hold y steady as a single number, then in the xz plane we get z equals c plus x squared, and those would be parabolas. So let's first look at the yz plane. So if we look dead onto the yz plane, and notice these graphs are drawn a little strangely, the yz plane is the one on the left. So if you look at the graph straight on towards the yz plane, the first one, 12.272, those traces would look like upside down parabolas. And in 12.228, the traces, if you slice, in other words, you're slicing perpendicular to the xy plane and parallel to the zy plane, you would get W shapes if you're just looking at the zy plane. And that would be a 4th degree polynomial, not a cubic. And then 12.229, now that one, if you slice it with a zy plane, those do look like cubics. So that's a possibility. 12.230, you would get lines if you slice it parallel to the zy plane. And 12.231, you would get upside down parabolas. And 12.232, you would get right side up parabolas. So it pretty much has to be 12.229. But let's just double check and look at the xz plane. And the xz plane would be the one on the back right hand corner. And so if we double check our 12.229, yes, those do look like parabolas. So we can conclude that the correct graph is 12.229. So now that's the end of your lesson for 12.2, and it's your turn to do some problems.